Hello, everybody. I have so many buttons to push. You don't have any idea. Hello, everybody, and welcome to Telescope Talk Pro, a hangout designed to let you know about all the amazing happenings in the world of professional ground-based astronomy from all over the globe. My name is Tony Darnell from deepastronomy.space, and I'm very excited about today's hangout because we're going to be talking about ESO, the European Southern Observatory. It is the foremost intergovernmental astronomy organization in Europe and the world's most productive, they say, astronomical observatory. I'm going to ask them about that and what that means here in just a minute. We're going to talk about that. So ESO provides state-of-the-art research facilities to astronomers and is supported by Austria, Belgium, the Czech Republic, Denmark, Finland, France, Germany, Ireland, Italy, and the Netherlands, Poland, Portugal, Spain, Sweden, Switzerland, and the United Kingdom. How about that? In alphabetical order. Along with the host state of Chile, which is where a lot of, I think maybe all of their observatories are. So, I just got a thing from Peter Quinn saying loud and clear. Phew, what a relief. Today we are joined by Doctors Today we are joined by Doctors GAITEE HUSSAIN and RUBEN SANCHEZ-JANSSEN to discuss some of the amazing work being done at ESO and get us familiar with some of their instruments. Now, you may have heard about the big news, I think, that came out just day before yesterday, or maybe just yesterday, about the unprecedented observations of material falling into the supermassive black hole at the center of our galaxy, lovingly known as SAG-A-star. Not to be confused, by the way, with SAG-A-star. Okay, it's SAG-A-star, or SAG-A-star, or Sagittarius A-star. We'll also talk briefly about those observations made with the gravity instrument on the Very Large Telescope. So let me go ahead and bring up everybody. My co-host from these hangouts is Christian Reddy from his YouTube channel, Launchpad Astronomy. Where did my cursor go? There it is. There we are. And there they are. Okay. Hey, guys. Hey, Christian. How are you doing?
Hey, Tony, fine. Doing great. I'm glad to be back here on Telescope Talk Pro and really looking forward to our conversation today with our guests.
Good. Yes, me too. And so let me go ahead and introduce right next to me in our little astronomical Brady Bunch, like I said, is Dr. GAITEE HUSSAIN. She is an astronomer at the European Southern Observatory. And right below her is RUBEN SANCHEZ-JANSSEN, not from the Royal Observatory, as I originally wrote down. Well, he is there. He's physically there, but he's also part of the UK Astronomy Tech Center. So welcome, guys. GAITEE, let's start with you. Can you tell us a little bit about ESO? Just give us a big overview of who ESO is and what they do.
Sure, happy to. So ESO is just over 55 years old, actually. So it started off with an agreement from the original 5 member states. So that was in alphabetical order, like we did earlier. Belgium, France, Germany, Netherlands, and Sweden. And the idea was that they from the original 5 member states, so that was in the Hemisphere, that was a great observing site, and they would build a sort of 3-meter class telescope, which at the time was very big. So it was the 1960s, remember, and but also encoded into the DNA of the organization from the beginning was this idea that ESO should also serve as the center that helps coordinate astronomical research for the member states, and also with the idea that we would do it for Europe eventually. So that was relatively successful. Fast forward 55 years or so into 2018, and as you listed, we now have increased in size, or tripled in size, just in terms of member states. So we have 16 member states now. Ireland joined this year, which was very exciting for us, and we have various observing sites in Chile. So if you could pull up the ESO intro site thing in Google Drive.
Which one was it?
It was the ESO intro site telescope. There's various pages on
yes. I got it up. Hang on. It is now up. I am
okay,
I am
so
showing
I'll
that.
just pull it up here so I know what I'm talking about. So here what you see is a map of South America, and hopefully.
Yes,
and
they do see it.
Because I can't see it from here. So there are marked along it sort of 3 red dots, if you can see them, which are La Silla, Paranal, and Chajnantor. And those represent the three main observing sites that ESO either operates or helps operate in partnership with other organizations and consortia. So where ESO's origins are is in La Silla. So in the beginning, they looked for fabulous observing sites in the Southern Hemisphere. And the reason they wanted to go south was because you have this beautiful, advantageous view of the Milky Way for several months in the year. And you also have access to the Large Magellanic Clouds and the Small Magellanic Cloud. And so there were various astronomical objects of interest that they really wanted to target. So they looked in South Africa for a while, but then they realized that actually Chile was a really great place to go. And so all of our observing sites now are essentially at some point along the Atacama Desert, which is what's sort of shown here in this map. And so the Atacama Desert is basically the driest place on Earth. And what's more, especially at the observing sites where we operate, they're some of the most stable observing conditions you can hope for. So, so that's kind of where we're at today.
It's also very dry there because it's in the desert. There's very little water vapor, which is important, isn't it?
Yes, absolutely. And so actually, so near La Silla, there's two other major observatories. There's CTIO and there's Las Campanas, which are both sort of US based. And that really shows that a lot of worldwide astronomers about the same time decided to decamp and go to the same part of the mountain range. Paranal was discovered later. Tony, if you could just move down to the second page in that collection.
I'm there.
Yeah, so here you can see a satellite image, and you can see the positions of where the VLT is where the Paranal site is, which is kind of our flagship observatory right now. It's where operations are very much concentrated and where most of the activity is concentrated. And you can see ALMA, which is the other site that we help operate. So ESO is also the European partner in the Atacama Large Millimeter Submillimeter Array. And Chajnantor, where ALMA is 5,000 meters altitude. And so it is extremely dry and above essentially most of the clouds that you'd worry about. And the satellite imagery really shows that even while you have clouds butting the coast of Chile, they're not really going to affect an observer.
I know it's like this little island of clearness around all of these. Look at those clouds everywhere, and except not where these observatories are.
GAITEE, just to clarify something, you mentioned that ALMA. So that ESO is the largest partner in ALMA, and ESO, of course, is it's a partnership of several countries. So who else other than ESO is involved with ALMA?
So I don't know if it's the largest partner, but it's the European partner in ALMA.
I gotcha.
So,
Okay.
so there's North America, there's Japan, there's also, and I think that's essentially it. RUBEN?
No, it's those three. Yeah.
Yeah.
Okay.
Great.
All
So
right.
truly international collaboration.
It's a very international collaboration. So we have ESO employees that are essentially working for ALMA full time, and similarly from the North American side and the Japanese side. So it's a very interesting, very, very international collaborative atmosphere. It's
Excellent.
And in fact, ALMA itself, the whole observatory, there are antennae that were built on the European side, there are antennae that were contributed by the North Americans, and antennae that were contributed by the Japanese, and they are all subtly different. So it is a true collaboration in terms of people and hardware and everything.
Okay, I forgot to mention this at the top of the Hangout, but these images that we're showing you and the graphics that are coming up throughout this Hangout are all available to you. The link is I have them on a Google Drive folder, and the link is in the description box on YouTube, and I will post them on Facebook later. But for now, if you want to get at them and look at them yourself locally, because I'm not always sure how, especially the quality of the text goes through on the stream. So these are all available in the description box below. We are also streaming, by the way, on YouTube, Facebook, Twitter, but I'm not doing Twitch today because I couldn't get my stuff together. So we are I'm checking all of these comments and stuff like that. So okay, RUBEN, let me bring you in here and tell us a little bit about what you are doing at ESO. You're located in Edinburgh, so tell us a little bit about what you're up to.
Yeah, so I'm actually not an ESO employee. So I'm part of the UK Astronomy Technology Centre, which is the UK's national laboratory for the design and development of astronomical instrumentation. But the UK is a member of ESO, and as such, the astronomers of our community have access to time on those telescopes and also help develop instrumentation for the observatory. Well, in the past, in my particular case, I was lucky enough to actually have worked at ESO for my first postdoctoral experience. So I spent 4 years working in Chile at the Paranal Observatory. And then I moved on, and for the past almost 3 years, I've been in the UK. So at the UK Astronomy Technology Centre, what we do, as I said before, is develop instrumentation for mostly ESO facilities. So that's basically all the cameras and instruments that go attached to the telescopes and actually complement them and make them the powerful tools they are for astronomical research. So in my particular case, I'm what's called an instrument scientist. So I'm kind of at the interface between engineers and astronomers, making sure that whatever engineering decision is made doesn't impact the science that we want to do with these instruments.
My kind of guy. I was a software. I don't have a PhD, but I worked as a software engineer, writing code for and helping to build cameras, and so I'm very much a hardware guy too, software guy. So I love the fact, that there are people who can bridge the gap. And if we have time, I have a question about this sort of the training that goes in between astronomy and astronomers and engineers, but I'll do that if we have time. Okay, well, I want to talk a little bit about let's start with some of the instruments that you have. No, I'm sorry, not instruments. Telescopes that you have up in the high in the Andes Mountains, and I want to start with the VLT. I have the graphic that you sent that shows the VLT. This is a big complex. Who wants to talk about it?
So is this the VLT image?
Yes.
RUBEN, do you want to take this one?
Sure, yeah, why not? So yeah, so actually that image is a sketch of how the Paranal Observatory looks like. So it's not just the VLT.
Right, I'm sorry.
Telescopes.
The entire complex.
Yeah, that's fine. Yeah. So Paranal is as Tony was saying, is a complex site. It's not a simple one, and you can probably see there depicted 4 very large telescopes. Those are what we call the UTs. So each of those are 8.2 meters in diameter, and they are pretty much almost identical. Then also you can see 2 smaller telescopes on the top right, the VST and the Vista telescopes. Those are smaller telescopes, 2.5 and 4 meters respectively, that are actually used to carry out surveys. So they mostly carry out imaging surveys of the southern sky. And then there's in front of the VLT at the platform is the VLTI, which is the VLT interferometer that basically combines or can potentially combine the light of the 4 UTs together with 4 smaller, what we call auxiliary telescopes. So yeah, Paranal is right now 7 telescopes simultaneously, and they are operated from the same control room up there on the mountain. And so what I was mentioning before about the instrumentation, what is quite unique about Paranal, or the VLT in particular, is that, as I said, the 4 telescopes are identical, but all of them have 3 instruments mounted. And so simultaneously, on a given night, you could potentially observe with 12 different instruments on 8-meter telescopes, right? So the breadth of science you can carry out in a one single night is really, really amazing.
Thanks for pointing that out, Ruben, because I always had a question. I had actually several questions about how VLT actually works. We have the 4-unit telescopes. Then you have 4 auxiliary telescopes, right? And I was wondering if you could describe how they play into, what role do they play?
So the VLT is quite unusual in that the idea of it, even from the beginning, was that it should work together as an interferometer. So you could either use the 4 UTs together, and you could see they're sort of put in this particular shape, and that shape of the exact positioning of the 4 8-meter telescopes is very particular. So that combined, if you combine all 4 of them together, you have the same angular resolution as if you had a telescope with a diameter of 130 meters, which of course is somewhat technically challenging if you were going to do it in one single telescope. But with the 480s, the beauty of them is that you can move them around. So they're much smaller. They have 1.8 meter mirrors, I believe. And so with them, you can essentially move them around. You can have different baselines. And so you can, you have much more flexibility. And so the interferometric instruments that we offer can be used either with the 80s or the UTs. At the moment, but the idea is ultimately you should be able to combine both. In fact, even though the VLT had its first light about 20 years ago, it wasn't until 2011 that the light from the 4 UTs was used from the 4 8-meter telescopes was actually combined together in an interferometric instrument. That was with Pioneer. So it took a while to actually use all 4 together, but until then, 2 or 3 of the telescopes were used together fairly regularly.
Okay, so the smaller unit telescopes they're small for the purpose of being able to move them around. Obviously, I think it would be a lot more difficult to move an 8-meter telescope around, right? So these are small, intentionally smaller to be movable, not portable, but movable.
Yeah.
And I also noticed that the Unit 4 telescope is equipped with an adaptive optics system. Do the other unit telescopes have adaptive optic systems, or if they don't, do you know if there's plans to upgrade them to give them AO?
So all of the telescopes have been designed to have active optics, so that what that means is that the primary mirror has these actuators, sort of these control things underneath them that can adjust the shape of the mirror to account for fluctuations in thermal environment and other effects. So there are wavefront sensors. So there's some active optics applicable in all of the 8-meter telescopes. However, with UT4, what we call YEPUN, which is its indigenous Mapuche name, we recently had commissioned the laser guide star facility, which now is supercharged. It has 4 sodium lasers that allow us to correct for atmospheric effects. So the short answer to your question, I've already made it quite long, is that no, we won't be installing the this 4 laser guide star facility in all 4. But there are adaptive optics in several of the other instruments. So NACO, for instance, on UT1 has a form of adaptive optics in the wavelengths that it works in, as does Sphere. It's just not using laser guide stars. And so
right.
there are reference guide stars that we can use as wavelengths.
Right. You only need to use the lasers when you are lacking a bright reference star in your field of view. Do you happen to know, or did you already say why there weren't plans to install laser stars on the other telescopes?
I believe it's just technical. I think it's cost partly, but it's also because, some of the instruments really benefit from it hugely. Some of them don't necessarily need it.
I see.
So the instruments that are in UT4 very much, so Muse is benefiting hugely from this. In fact, there is an image in Google Drive, which, what is it called now? I think it's called, yes, Muse LGSF. If you can pull that up, Tony.
Okay.
You can see what happens when you turn our adaptive optics on and off.
It is on and it is up. So.
Using Muse. So this is in the narrow field mode. It has the best spatial resolution.
Right.
And you can see these pictures and what happens to Neptune before you put on the adaptive optics and when you put on the adaptive optics.
Yeah.
And so now from the ground, we're actually reaching arguably better spatial resolution than you can do from space with Hubble. I mean, the image taken with Hubble was not taken at exactly the same time, obviously, but you can see the comparison of the level of detail that you can achieve. So the narrow field mode is amazing, and it will do incredible things with news.
This is astonishing. I'm sorry to interrupt. Go ahead and finish.
Yeah. No, sorry.
I agree. It's amazing.
Well, I'm just looking at these 4 images, and if you don't do anything, you get this big blue fuzzball. This is Neptune, by the way, right?
Yep.
So these are images of Neptune. If you turn on some adaptive optics, and you get what's in the upper left, and then what the VLT can do. I mean, either one is still better.
Yeah,
oh,
the top left and the bottom left are the same.
Oh, that's the same image. Okay.
Yeah. And then that's just the comparison with Hubble.
And look at that. Look at that. And this is from the ground.
That is amazing.
So an argument can be made then by some, and I'm sure it's being made by many, that they don't need space telescopes anymore to do a lot of this resolution. But there's other things you get from going into space. But
I wouldn't go that far.
So what's the catch? What's the catch of adaptive optics so far?
You still need good conditions. I mean, it's not, you couldn't do it every night. There are certain seeing conditions you'll need. There's certain, there's still weather that you have to balance. But also with space telescopes, the advantage you have is that you can point it, depending on the space telescope, you can point at almost anything. You're not so much restricted by the natural visibility window of where you are at night. So there are huge advantages still to go to space. And also, I mean, there's much cleaner observing windows in space than there are.
And am I right in understanding that the adaptive optics currently are our current ground-based technology? Well, adaptive optics is ground-based, but that it's primarily at near infrared, that we don't really have a viable AO system for visible and visible light, correct? Or am I wrong?
I'm not sure. RUBEN?
Okay.
Well, so it's true that as of right now, we only can carry out the level of corrections that would make a telescope let's say, comparable to Hubble or competitive against Hubble in the infrared. So that's absolutely correct. But our technology is improving, and actually we're moving the, say, cutoff, or the cutoff wavelength of active correction towards the blue end of the spectrum more and more. And so actually ESO has plans for the future to actually build an instrument that makes use of this AOF, the Adaptive Optics Facility, to actually carry out corrections at the wavelengths comparable to the red light, let's say, of the visible spectrum. So not just infrared, but moving already into bluer wavelengths. And that will make it more and more similar to Hubble. So yeah, the main problem, on top of all what GAITEE mentioned, is that first, Hubble can get, and that's why we still need space, and they're very complementary. Hubble can get very, very, very precise or high acuity at the blue end, or even ultraviolet light. We cannot do that from the ground. And the other difference is that to make that comparison and to see the two pictures that we're showing right there, remember that Hubble is only a 2.4 meter telescope, whereas the VLT is an 8.2. Right? So we're getting rid of the atmosphere and taking advantage of the big aperture. Still, Hubble is a much smaller telescope that is providing amazing, superb image quality with such a small aperture, only because it's in space.
Okay, so I want to get to a couple of comments here, if I can. They start. Some of them have scrolled up here, but let's see. Mad End wants to actually. Before I do that, where did it go? Adam Synergy. He just wants to say that the VLT sphere and gravity instruments are awesome. He just wanted to say that. So yeah, I agree. We'll talk a little bit more about gravity in a sec. Let's see. Mad Ed wants to know, as the space is limited, what will you do when we run out of mountaintops for telescopes in Chile? There's a lot of mountaintops in Chile. Any comment on that, guys?
So I think eventually you could run out of pretty much everything. That's certainly true. For the foreseeable future, there we have big plans, and you can see. I mean, we haven't mentioned the ESO's extremely large telescope project.
I know we're going to get to that.
So there's a neighboring peak at which we've already started building essentially the next massive project, which will be the largest near-infrared optical telescope in the world when it comes to light in roughly about 2024. So we're not short of space yet. And our Chilean host country is extremely open to us collaborating with them. We try to keep very close collaboration with them at every stage because it has to benefit Chilean science as much as it benefits us. And so that is a key part of it as well. So we have to make sure that both of those sides of the equation are working.
Yeah, that's a good point. Hans Milling is asking a question to all participants, including Tony. Have you ever been to any of those sites? Have you guys ever been down there? Oh, yeah.
Yeah, well, I spent 280 nights working. So
yeah. And I haven't been to Paranal, but I have been to CTIO with the Blanco 4-meter, and so that was a great experience. I was there for about a week. It is so weird, folks, and I don't know, maybe Paranal, maybe you can comment on this. The life of an astronomer on a mountain is really weird. There was a complex for sleeping, apartments that you sleep in while you're there, that have these power drapes that come down. Actually, they're shutters that come down, completely block off all light in the room you're in so that you can sleep after a night's observing. You do that for about a week and you are messed up. I mean, you get up at 3 in the afternoon, 4 in the afternoon, you have breakfast, and then you go and you get ready for your observing, and then you stay until the sun comes up. It is, I mean, am I right, guys? I mean, it is a strange set of schedules you have on these mountains.
It's the best thing on earth, frankly. It's amazing. I miss it.
Yeah, it is. It is nothing like it on the and there's also nothing like the work environment, right? You just look up.
Absolutely. I mean, you meet people from all over the world. Everyone's there. Everyone's super excited. You meet young students who are just on their first observing trip, and they're so excited. And you just get enthused about astronomy all over again.
Yeah.
And for me, I think the favorite moment is at the end of an observing night. You're completely tired and you're walking back up the mountain and dawn's sort of rising around you, and you're just, it's just spectacular.
Wow.
Especially in Chile, it's the best thing.
Yeah, nothing beats a sunset or a sunrise at the desert.
Very true. Very true.
The advantage of working on a space telescope is that you can just wake up in the morning, go to work, and then go home at night like everybody else. But yeah, I do miss that. I do miss those observing runs on the mountain. That was Kitt Peak is as exotic as I've ever gotten.
One of my favorite observing ones actually was at Keck, if I may be slightly treacherous towards ESO. But I remember...
That's on Mauna Kea, if you don't know, guys.
Because so this was in the Big Island in Hawaii, and we were using the ground observing station in Hawaii. So it's in Waimea. So you'd wake up at 2 o'clock or whatever. You'd go to the local beach and have your breakfast, and then you'd sort of get started for the next day. It was incredible. It was the best.
It's hard life. What we all the sacrifices that you make. Taya and GAITEE just gets me here.
Yep.
So I think we were talking, or actually, Tony, were there any other comments or questions that we wanted to get?
Well, no, but go ahead and get started. And then I have a.
Well, I wanted to turn our attention briefly to the extremely large telescope. Since
no, I don't want to talk about that yet. Hang on.
No, we're not going to talk about that.
I do want to talk about the ELT. I promise we'll get to it.
No.
I'm going to go back to.
You don't discuss ELT.
Yeah, we will. We promise. I just want to finish up what we're talking. In particular, I have a question about Vista. You made a comment, Ruben, earlier that it is a survey, one of 2 survey telescopes. What's the difference? And what kind of science can you do from what's so great about a survey telescope? Because we've got a lot of survey telescopes coming out. There's the Dark Energy Survey. That's at CTIO. There's the Sloan Digital Sky Survey. That's in New Mexico. There are lots. And there's LSST coming up. That's a survey. What's the difference, Ruben, between a survey telescope and what these other ones, these 8-meter telescopes on the mountain, do?
Yeah, so the main difference is probably the way in which they are operated. So on regular telescopes, basically astronomers submit proposals to actually carry out their science, and they either go to a telescope and observe for their own science for a number of nights, or those observations are carried out for them, which is a typical observing mode at ESO. It's called service mode. So you're at your home, you submit whatever you want to get observed, and then the data is in an archive, so you can download it. You don't have to travel to Chile. But for survey telescopes, what we actually do is that we're only observing a predefined let's say science or patches of the sky. In this particular case, VISTA is an imaging telescope. There can also be spectroscopic survey telescopes, but VISTA and the VST are imaging survey telescopes. And what they do is that they cover large areas of the sky to any given depth that actually will serve a particular purpose or so they will address one particular science case for which a huge area or a very deep field are required. So the number of, let's say, programs that are executed on a given night on a survey telescope is smaller than on a regular telescope on a given night. But of course, those surveys, imaging surveys in this case, will actually provide data for a lot of different science cases.
Yeah, because when you're staring at the whole sky for a long time, and you're building up, like you said, depth, we're just seeing very faint things, a very, very high magnitude or very dim. High numbers generally mean dim things in the magnitude scale. You can use that for a lot of stuff, and you could find transients, for example. You could find exoplanets. You can find asteroids. There's lots of different kinds of uses for that sort of data. So. Okay, good. I wanted to make that distinction because these other telescopes are sort of, I always call them point and shoots, right? But you have to make a science case for what you want to observe. You have to get approved. Say, yeah, okay, your science case is good enough. You can have one of these giant telescopes for this long to do your survey, and you'll get your data and you can write your paper. That's a very different use case than survey. So I wanted to talk about that just a little bit, and that is with the VISTA instrument. There's another one. What was the other one? I forgot.
VST, so that's a VLT survey telescope, which is more in the optical wavelengths.
I see.
So VISTA is actually kind of coming to the end of what it was designed to do in terms of being an imaging survey telescope. In the next couple of years, it's going to be transformed into something called Foremost, which is a consortium that's working closely with ESO. And they're going to convert it into a spectroscopic survey telescope. So it's going to have thousands of fibers through which you can actually get spectra from, it's going to cover a whole range of science objects and science cases, essentially. And it's the field of view it's going to cover is about 4 square degrees.
Wow, that's big. That's a big field of view. By comparison, the full moon and the sun, the disk of the sun, is a half a degree. So that is a big field of view. And what's the advantage of spectra? All these okay, no, I'll stop there, because I know Christian wants to talk about the ELT. So that was one point I wanted to make. So Christian, he left.
I think he said he'll be right back.
Oh, he went away.
Just left us a message. Yeah.
Oh. Well, okay. I was going to let him ask his question about the extremely large telescope, but instead, I will go to spectra. And I think that's related to the gravity instrument, right? Can you tell us a little about why spectra in these fiber optics are so important?
So spectra give you a lot of information. So images in different filters can tell you you can already use them to judge something about the temperature of what you're looking at. You can also try and derive some other properties, but you really need spectra to understand the motions of what's happening in the targets you're looking at. So for instance, if you're looking at high redshift galaxies, you're looking at the early universe, you can use spectra to actually look at rotation in those galaxies. You can actually see rotation in those galaxies because you can see these blue shifted and red shifted lines essentially at different points across your galaxy. I think we have a KMOS slide that sort of shows this.
Okay.
So this is just all of the splodges shown here are all different galaxies of different redshifts, going from about 0.5 to 2 redshift. A redshift of 2, and the blue and red really show you that essentially you've always got sort of an approaching edge of your galaxy and always a receding edge of your galaxy, and this is what spectra give you. They're enormously powerful, so they can tell you the motions in the galaxy. They help with diagnosing dark matter. Ruben can tell us a lot more about that because this is much more his science area than mine. I'm much more stellar and exoplanets. But for exoplanets, their spectra are particularly interesting because they tell us what the composition. They will tell us when we're there what the composition of their atmospheres look like, and so we'll be able to actually understand how many clouds a giant planet has, like a Jupiter-sized planet has, and what's more common, and how and compare it to what we see in our own solar system. So spectra are enormously powerful, but not as pretty to look at usually.
Well, I don't know.
So
That's
Tony, can I ask you? Can you put in the moon's picture? So
okay, it is now up.
Yeah, so following up on what GAITEE said, so moons is another multi-object spectrograph that we actually are leading here at the Education Astronomy Technology Center, and highly complements FORMOST, which is the instrument that GAITEE mentioned. So the difference between the two instruments will be that FORMOST will be on a 4-meter telescope with a much wider field of view, and providing spectra for a couple thousand objects, whereas moons will be on the Naismith focus of one of the VLTs. So it will take advantage of the 8-meter aperture and will provide spectra simultaneously for 1,000 targets. So that, as she said, will provide not only kinematics but also chemical information of stars in our own Milky Way, and galaxies at very high redshifts in large numbers, so you can actually beat statistics.
Okay, now there's so much to talk about here. I've got the KMOS thing back up again because I just want to make sure I'm visualizing it correctly. Every one of those splotches that has red on one side, blue on the other, that is an output from a fiber optic cable, right?
Not exactly. So there's no fibers involved in KMOS. KMOS is a multi-IFU instrument that actually has 24 arms that deploy what we call image slicers. So basically, it's an integral field unit, but it doesn't use fibers. So the throughput is actually quite good. And so it deploys 24 arms, and on an aperture of about a bit less than 3 arc seconds across, you get multiple spectra of individual objects. So as GAITEE pointed out,
so these are individual objects that are actually rotating in the direction you can see by whether it's red, it means that side's going away, blue means it's coming towards us, and you by the magnitude of those numbers give you information about the velocity which is doing that.
Indeed. So you are spatially resolving the objects. That's the difference between the multi-IFUs, the integral field units, because you have spatial information every time you point to an object. When you go and do FORMOST or moons, you won't have spatial information. You will be collecting all the light from that object, but you don't know how that light is distributed.
Okay. And so back to moons, that in the lower right corner, that is I can't see it very well in the way I'm looking at it. So that is the output of the spectra and what it will see.
So the lower right corner, what it shows is what's going to be the geometry of the focal plane. So basically, if you see on the right, there's like that's the optical fiber. That's the peak-off that will collect the light. And there will be 1,001 of those that will be pointing upwards, that's basically the plate that you see slightly on the left. So 1,000 of those fibers will be patrolling the entire field of view and putting on fibers on different objects to actually collect their light.
Okay. Wow. I zoomed it up just so I could see it better. Okay. Good. All right. Well, gosh, we're running out of time. Okay. Let's talk about the ELT. Go ahead, Christian. Bring it up.
VLT, right.
Yeah. We have the very large telescope and we have the extremely large telescope coming up.
Oh, I'm sorry. Extremely large telescope, ELT, right. So tell us a little bit about what you're working on in particular. I understand, Ruben, you're working on ELT. You're doing some work in GAITEE. I don't know if you are as well, but if either of you are doing work, just describe it for us, please.
GAITEE, do you want to start with what's the ELT, and then I'm
going to put the foundation picture up.
Sure.
I've got that up.
Yes, exactly. I was just going to
go ahead. Go ahead. All right.
So this is a picture of neighboring mountain peak to Paranal, and this is a picture just taken about a month ago. So you can see what's happening there, and you can see the foundations are being laid for something that is absolutely massive. So you can see these tiny trucks in the background, and those are fairly massive trucks.
That's amazing.
You can't even see the people, and there are people somewhere in that picture.
I'll take your word for it.
It is huge. In fact, there's some great images. I'll see if I can put one in the Google Drive soon, which compare the size of what the ELT will be to massive worldwide landmarks, and it is fairly impressive. So it's going to have a primary mirror with 39 meters diameter. So it's a huge step up, and it's very ambitious, and we are well on our way. It is funded. And so the first instruments have had, at least some of them have passed their preliminary design reviews. So they're being built. Ruben's involved in that very heavily. And so we seem to be on track, basically, to have first light in 2024. And this is something that our member states have all agreed that they want to do. So they've given contributions in order to fund this. It's not cheap, but it's going to be amazing.
It is. It looks amazing. And
0.3 billion or something euro.
It's close to that. So.
Wow.
Okay.
Remarkable.
Yes. So where was the question I was going? Oh, TGM Ryko wants to know. Let's see. What about La Silla? They have HARPS there, the most prolific ground-based planet hunter so far. You want to talk about HARPS?
Indeed. So I am an avid user of HARPS, as I think I know who asked that question, actually. But
oh, okay.
So HARPS is very precise radial velocity spectropolarimeter. So not only can you get very, very precise, very stable spectra over a time span of many years, up to decades. So that's very important in order to be able to detect the reflex motion due to planets orbiting around stars. So it's been used to do follow-up, for instance, of transiting planets that have been found with Kepler, but it's also been used very effectively to find planets in their own right. Something that's really cool that HARPS does as well is it can also show us the polarized light coming from the star. So not only do we get the radial velocity measurements, but we can also detect magnetic fields at the surface of the star. So what we can begin to do is we can start understanding the environment in which these planets are having to evolve and survive. Because that's a big question particularly in terms of habitability. So if you have a very magnetically active star, if you have a star that's not as old and complacent as our own sun, then that has important implications and quite devastating potentially implications for the evolution of complex life. And HARPS can do all of that. Now, we have Espresso that has recently been commissioned on the VLT, and that is a very interesting machine in the sense that it can be used on any of the individual unit telescopes themselves, so any of the 8-meter telescopes, or you can combine the light from all four. And it's essentially going to be the new HARPS. But the real advantage of La Silla is that because it's a smaller telescope, is you can really start exploiting the time domain. So you can really get long-term sampling of activity on stars, which you really have to start worrying about if you want to get down to Earth-sized planets.
I don't understand why how being small helps you with that. Just
well, it's just because you can get long chunks of time on it.
Oh,
so it's very
I
hard
see.
to get. It's very hard to get 2 weeks on an 8 meter. It's extremely expensive, and you have to really have you have to have like a Nobel Prize winning case at the moment. With the VLT coming, maybe at some point we'll be able to get 2 weeks on the VLT to just.
The VLT will suddenly get cheaper. Yeah.
Exactly. So the cases will change, but I mean, we're really starting to push up against this problem of stellar activity in order to find planets, and we really have to understand the weather on the star itself in order to be able to detect planets. And so that's something that HARPS is doing spectacularly well for us.
That's actually
well. I should also point out that we're already hearing. We have some folks in our chat room saying, "Yeah, planets. What about moons?" Right. So we're we're on the bleeding edge here at Deep Astronomy. Can HARPS assist in searching for exomoons, do you think?
It would depend. It would depend how big the signature is. It would depend on what kind of period it is. But yeah, I mean, sure, you could. We're down to essentially below the meter per second level almost with HARPS. So in fact, we can do it with laser frequency time. So we can do it. But it's but our problem is stellar activity. Really, our bigger problem is not technically what we're doing with the instruments. We can do amazing things with the instruments, and there are different ways of calibrating out systematics. But you can't control the star itself. And that's really important for us to be able to understand, particularly because the next lot of planets that we're going to find, what TESS is focusing on, what a lot of the planet-finding missions are focusing on, are planets around M dwarfs, and M stars are extremely magnetically active compared to the sun. I mean, there's different definitions of that, but so we have to worry about magnetic activity quite a bit.
Okay, so you're telling me that HARPS and the ones that's going onto the 8 meters later, you can measure and differentiate the magnetic field of that star in a way that not only gives you a map of its magnetosphere, but also things like active regions and stuff like that. Right.
So yeah, so we have this great technique. It's called Doppler imaging. It's sort of based on.
It's called what? Can you say it again, please?
It's called Doppler imaging,
Doppler,
and it's based on. Yeah, it's based on the same kind of principles used for medical imaging, like MRI and stuff. So essentially, you use spectroscopy, and you allow the star to rotate, and you're essentially taking like slices of the star as it rotates, and then you back project them, and you produce these amazing maps of the active regions on the stars. And then you have to use the same kind of techniques we use for the sun to extrapolate them and understand what the extended atmosphere looks like. So that involves a bit of modeling and a few assumptions. But you can resolve the surface of the stars using these indirect techniques.
That's amazing to me, because we don't even really do that with our own sun. I worked at the High Altitude Observatory for a while, and we did not have a good way to measure. We did it with like you said, with polarized light, but it was hard to get the magnetic field of our own sun. So we even that measurement for a star that's right down the road is extremely difficult to make. So I'm just amazed that HARPS and instruments like that are able to get this kind of detail from other stars. It's one, and I suppose you can also get something called seismology information from it too. Then, right?
Yes, yeah, absolutely. So if you can combine all of those things, you have an amazing characterization of the star, which helps you then characterize the planetary system around it and maybe the moons.
Okay.
Ultimately.
All right. So, we only have a few minutes left, and I got to get questions too. Ruben, me and you, man, for just a minute, okay? I love the fact that you work in instrumentation, and I get a lot of students, and I try to give vlog posts and advice on starting a career in astronomy. And one of the things I always give advice out to is, do not think that you have to become a PhD, capital A, astronomer to get a good job in astronomy. I've always advised that if you can build things, if you can program things, if you can put, design things that hold other things up, mechanical engineering and things like that, then you are in demand. That is a skill set that can be used in astronomy quite a bit. I have had zero problems finding jobs as a software engineer. I also had experience building a camera, an infrared camera. That experience in a clean room really helped me with working with hardware. Would you agree with that statement that you could get a job that isn't necessarily a PhD level job working with equipment and instrumentation and helping to design them? Would you agree with that characterization?
Absolutely, absolutely. In my case, I am an astronomer and I do hold a PhD.
I know you're a capital A astronomer, but you also bridge that
what
gap.
I mean is that at the observatory, let's say Paranal, right? There's on a daily basis, there's almost 100 people working there, out of which about 15 are astronomers. The rest, among also like local personnel, there's a lot of people doing all sorts of work for the observatory. There's software engineers, mechanical engineers, optical engineers. So you can definitely be at the forefront of science and technology development without a PhD. Well, of course, you must like engineering, you must like hardware and or maths, but definitely there's a ton of opportunities out there if you're really passionate.
Okay, and Christian, I'd like to get your feedback on that too. You teach students every day. Would you agree with that assessment? Do you find that there are people who would maybe get somewhat despondent about a PhD, but would gravitate toward a career like that?
Absolutely. I mean, just to say what's being said here, there are so many avenues into the career path of astronomy, and I think it all depends upon what you care about the most, what interests you the most, what you enjoy doing the most. So, Tony, you were saying if you can build things, if you like to program, if you like to create things, software engineering. If you have a creative outlet, or if you like to communicate, there's teaching, there's public outreach. There's so much going on in this field, and it's getting bigger all the time, largely thanks to these incredible instruments that ESO is developing. So there's always going to be a need for people to help explore that. So yes, absolutely, there's no question about it. You can certainly find yourself a nice niche in the field, whether you choose to pursue a PhD or not.
Great. Adam Synergy says I need to get to some comments and questions here. Adam Synergy says, I've already got my beautiful ESO 2019 calendar. That's a good point. You guys make really nice calendars.
Yeah, I love your calendars.
Yeah, they really come out. John wants to know, as far as time on big telescope goes, does ESO collaborate with amateurs with adequate equipment for certain observations, or should it?
So certainly, I mean, we're plugged into some networks. There are amateur networks that, for instance, follow transients and things, and we certainly use information that they give us, and astronomers collaborate with them as well to devise plans here. But we also have a sort of outreach observing program as well that uses our smaller telescopes, usually in the Silla, and they essentially, if there's idle time or whatever, then you can get some beautiful images, and certainly we have our pictures of the week and stuff that come out that are largely based on those kinds of things. But yeah, I mean, certainly I think we're open to that. It's just it depends. I mean, obviously our telescopes cost money, and the member states pay the money, so it's usually for professional research. But there are some outreach initiatives, and our outreach department is very active, and they do involve people. And there are calls for ideas of observations you might want. So look out for those.
Yeah, upcycle electronics. First, a comment. We want more G-type stars, though. You were talking about red dwarfs. What advancements will we have with type Gs with these instruments?
So Espresso is very much geared to look at G-type dwarfs, because it's mostly in the optical. I mean, M dwarfs, you want to start going into the near infrared a bit more, to longer wavelengths because they're cooler. Yeah, with G-type dwarfs, our biggest challenge currently is that they are more active. They have a lot of jitter, what we call jitter, which is sort of just different levels of activity and granulation, all the kinds of stuff that are happening on their surface. So there's a lot of effort on that. I think it's coming. It will come. TESS will do it too. But dwarfs are easier. They're easier for a number of reasons, particularly if we're looking for habitable zone planets, because they're less massive, and so the signatures of Earth-sized planets just are easier to detect currently. So we're going to start there, also because they're the most popular stars in the galaxy. So it makes sense to start with our best chances of finding habitable planets. But yeah, absolutely, we are not looking for G-type star planets.
We're not doing it.
Exactly, we are definitely doing it. And yeah.
Okay, so Matt End is also commenting that Vista, going back to the amateur part of it, collected data for a citizen science project on Zooniverse. So they are contributing to citizen science. Peter Q asked this question. He's my Geordie friend in Newcastle in the UK, and I kind of want to know the answer to this too. What's going to happen to UK's membership with Brexit? Are you guys going to let them stay, or are you going to kick them out?
The member status is irrespective of what happens with the EU. So that was, in fact, the day after the Brexit vote, we all the employees at ESO got an email from management who appeared to be somewhat prepared for the result, saying that, don't worry, everything's okay. Our agreement is independent of that. So I mean, there's some issues that we probably want to wait and see about. I mean, there's possibly some research funding issues that might come in, but not in terms of ESO's funding so far. Ruben, though, you are in the UK. What would you like to say?
No. I just want to say that what GAITEE pointed out, that's correct, and that holds for the European Space Agency as well. So there's a lot of let's say research endeavors in which the UK is part of that do not depend directly on EU membership.
Yeah, there was a comment earlier about that to distinguish between ESO and ESA. ESA is the European Space Agency. ESO is the European Southern Observatory. So you're right. It's good to make that distinction. Upcycle Electronics is commenting, I work 12 shifts for night shift for years. I loved grabbing a 6-pack and sitting out on my apartment patio with everyone going to work at 7 a.m. Judgmental people are funny. That's true. You do get screwed up. I mean, it took me weeks to get back into the normal, because those little do the ESO facilities, are they like this? They just totally shut out the light.
Oh yeah, definitely.
So you're sleeping, you don't know. I mean, and then you get up, it's 3 p.m, and you're like ready for some bacon and eggs or whatever, and it's like,
yeah, it's true.
It is a different world. But you're right about the night skies up on Paranal. I've seen a lot of people doing time-lapse photography from there. Do you guys ever just go out and take your SLR and leave it out while you go to work?
Oh yeah, no, we have. I mean, a lot of ESO staff are actually astrophotographers, because how could you not be if you're in Chile? So yeah, they actually give us a lot of the images that we have on our outreach website. So yeah, they're definitely very into that.
Okay, well, I'm afraid we're out of time, guys. I'm going to have to stop. I did not get a chance to talk about the gravity instrument work with the supermassive black hole at the center. Listen, any chance we
also could go way more into ELT, I think. So
I know there's just a lot that we didn't even touch on.
So we got to fix that.
Yeah, is there any chance we can maybe convince you guys to come back one more time and talk maybe sometime in the new year or sometime around that?
Sure.
That would be so
Love
great.
to have you back.
Thank
We're only going to ask you live on the air.
We're going to put you on the spot, so your only answer is going to be, sure, we'll come back.
We'd love to have you back. This has just been a great conversation, guys.
Right.
Thank you so much.
Yeah, thank you very much. I want to thank all of you for watching. We're out of time. I will be back on Thursday. Actually, I'll be back tomorrow. Telescope Talk Amateur is coming back with Ian Lauer and myself. We're going to talk about stuff tomorrow. And then, of course, Carol Christian and I will be back on Thursday with Astro Coffee, where we are going to be talking about how exoplanets don't like heavy metals. And so that'll be the Astro Coffee talk or topic for Thursday. So join us for that. I want to thank my sponsors, OPT Telescopes, for bringing these to you, making them possible. And I want to thank you all so much for watching. I want to thank my guests for being here. You guys were awesome. Christian, you were great as always, except for when you left. You kind of freaked me out there, man. You just got up and walked away. I was talking
a little emergency. I typed something in the in the Zoom chat, but I guess you guys didn't
Yeah,
see it.
I can't see it because of the way I've got it set up. But yeah, I was like, okay, let's talk about ELT, Christian, and there's an empty chair.
Oh, sorry.
Oh, okay. All right, guys. Thank you. Thanks everybody so much for watching. And as always, keep looking up.